Good morning, folks. Hope you're doing well. So here's lecture number 3 on evolution, and this deals with niches and speciation. So let's go ahead and jump right in. Let's start with a niche. What is the definition of a niche? Well, check this out. A niche is the part of the habitat where an organism slash species lives and the resources it consumes there. Okay, so that's a niche. And let's apply that idea to this picture here. Okay, so here's a habitat. This is called the temperate deciduous forest, which is the habitat that we live in here in Maine, the biome, we could say, that we live in here in Maine. And so in this picture, we can identify all kinds of different niches, right? A niche is defined by the biotic and abiotic factors that are part of it, okay? So let's go ahead and say tab defined by the biotic and abiotic factors within that habitat. Okay, what are biotic factors? Biotic factors are living things. Okay, what are abiotic factors? Well, abiotic factors are non-living things, right? So biotic factors, living things. Abiotic factors, non-living things. So, for example, in this picture here, let's start with the types of abiotic factors that might be present. Can anyone think of any? All right, I'll take this one. How about things like the available sunlight? That would be an abiotic factor. How much sunlight is available? Well, let's take this log, for example. There will be clearly a different amount of sunlight available on the top of the log than there is on the bottom of the log, thus making those two locations different niches. How about temperature? Temperature is a non-living factor that's part of a habitat. Where would the temperature be higher? Again, let's take the log as an example. Temperature would be higher on the top of the log than it would be on the bottom of the log. How about available water? Well, probably there's more water available underneath because it's dried out less, right? So any location that has a unique set of abiotic factors in this habitat could be considered a niche. Okay. Consider, a few meters underground all the way to the top of the forest canopy, right? All along there, niches are scattered about. Okay, so the idea is then that for every available niche, there is a species that has evolved to fill that niche. Okay, so let's say under the log is dark, damp, cold, and there's not a lot of species diversity there, not a lot of biodiversity. Okay, there will be an organism that has evolved to fill that niche to take advantage of the available resources there. Okay, that's why we care about a niche. And speciation then is the idea that as new niches become available, or as populations that had occupied certain niches for whatever reason no longer occupy those niches, other species adapt, evolve to fill those niches. Okay, so that's the idea of a niche. Okay, so now let's move on to this idea, which is, I'm going to erase that, which the next idea is this thing called speciation. And that just means the creation of a new species. Okay, so there are ways that this happens. There are common ways that this happens, one of which we talked about in the last video, which was, it's okay, I wash my hands. Also haven't left the house in like years, so anyways. One method of speciation we talked about in the last video when we talked about the predictable ways in which populations change, looking at the bell curve and then how that bell curve changes when evolution happens. Okay, one of those curve change types, meaning directional selection, diversifying selection, or stabilizing selection, is the one that leads to speciation, or the creation of new species, potentially. Which one would that be? That's right, diversifying selection. Okay, so we could say ways in which new species are created. Well, we could start with diversifying selection, right? What does that mean? That means that as that bell curve transitions into a bell curve that looks like this, right? If those new mini bell curves move farther and farther away until there's no overlap, that those two new sections of the population have the potential to become new species. Okay, so that's one way that new populations are created. Here's another way. There's one called the founder effect. Founder effect. This is when a member of a population leaves that population and goes, or let's say a few, maybe a pregnant female, let's just say, to make this example work. One pregnant female leaves a population, goes to a habitat where there are no other organisms of that same species, and starts a whole new population. Well, the point is the allele frequency in that new population created by that founder is not going to be the same as the allele frequency found in the original population, just because it's going to be based on the allele frequency found in the founder, right? The one who founded the population. So that's one way that speciation can begin. So let's say that new population has different allele frequencies, therefore adapts differently to its new habitat, and over the course of 100 generations, let's say those populations haven't mixed for 100 generations, the population founded by the one organism has a genotype and phenotype that is so wildly different from the population from which it emerged that they're no longer the same species. They can no longer create fertile offspring, either due to genetics or due to behavioral separation. That's sometimes a way that species are separated. Okay, so that's the founder effect. What's another way that species are created? We have genetic drift. Okay, and that just means that over time, randomly, the allele frequency, the distribution of alleles in the population changes. Okay, that just happens. It's just a thing that happens. Mutations, randomness, you end up with more of a particular, a higher proportion of a particular allele than you had 10 generations ago, and your population has changed, and eventually that could emerge into an entirely new species if that drifts far enough away, right? And remember, the Hardy-Weinberg principle was that calculation that p plus q equals 1, etc., was based on a lot of prerequisites, right? A lot of stipulations that really are not seen in real populations. And this is one example why allele frequencies just change over time in a population. That's just the way it goes. But should that genetic drift, should the proportion of alleles in a population change significantly enough, a new species could be created. Okay, what's another way that new species might be created? We have the bottleneck effect. Okay, and that idea is that there's been some significant disruption in the habitat or the population, and the population once had this many members, and suddenly it only has this many members, and these are the members that are then going to go on and create descendants for the next foreseeable future, because all the rest of them, let's say, died somehow. That's called a bottleneck, right? You had this many, suddenly you have this many. Clearly, the allele distribution in this tiny slice of the population is not going to be exactly the same as it is in the entire population. So the bottleneck effect is your allele distribution was, calculated with this population. Suddenly something catastrophic happened. Now your allele frequency and proportions are calculated with only this much of your population. Okay, that's going to lead to potentially a whole new species, just due to the fact that the distribution of alleles will be so wildly different. Okay, one more thing to show you here, and that is this idea of adaptive radiation, which is this picture here. Let's make that large. Okay, so adaptive radiation is, let's write that down. Adaptive radiation, and that's the idea that, let's get this one back. That's the idea that there's somewhere in the course of history, there's a time at which all sorts of available niches open up, and populations adapt, evolve to fit those niches, and you suddenly have a huge amount of new species. Okay, when has this happened? Well, the most famous one, this is not the picture here, but the most famous one that comes to mind is the Cambrian explosion, right? Which is 542 million years ago, when multicellular life really took hold on the planet. So for whatever reason, there was multicellular life at least 600 million years ago on the planet, but life started, let's say, about 3.5 billion years ago as single-celled organisms, mostly until 600 million years ago. That was the predominant life form here on the planet. And then somehow habitat characteristics changed on the planet in such a way that the opening was created for multicellular life to proliferate, and something like is pictured here happened, where suddenly all sorts of new species evolved to fill the suddenly available niches. Okay, that's adaptive radiation. It's just a whole bunch of niches become available in a relatively short amount of time, and species and populations evolve to fill those available niches. Okay, so that's it for this video. And next up will be, I don't know what will be next up. Anyways, that's it for this one, and we'll talk to you soon. Toodaloo.